Welcome to our channel Physics Cat. Okay, today I am going to solve the remaining problems of chapter 1, chapter 2 exercise Bohr Somerfield theory of hydrogen atom. Okay, fine. So I have already started. Video is already published. Okay, go and check. And today I will solve the remaining problem. So now check the first problem. Okay, what is given? That calculate the wavelength of the transition from a level for which n equal to 7 to a level for which n equal to 6 for quadruply ionized boron. Okay, the atomic number of boron is 5. Okay, and its Rydberg constant is given 5. So answer is also given. Okay, and I will advise you that don't be afraid by seeing this quadruply ionized boron, because you all know that Bohr model is always active for hydrogen-like atom. So if this quadruply ionized boron is not given, then you can't use the Bohr model's formulas. Okay. So finally, I am going to write a formula. Okay. And you need to know about this. I think you have already know about this, but for revision, I am writing again. Okay, fine. So from Bohr's model, what we know that the expansion for the series spectra of one electron atoms, hydrogen-like atoms. Okay, as when if you assume that the nucleus is infinitely heavy, then this frequency will be nu will be 1 by lambda equal to r infinity z square 1 by nf square minus 1 by n square. I think you are familiar to this formula. Okay, fine. If I have already said the infinitely heavy nucleus, if you take it finite mass of the nucleus, then this must be written as nu equal to 1 by lambda equal to r infinity z square, okay, 1 by nf square minus 1 by ni square. So ni square. And now I will work with this formula. Fine. So I am writing something. Okay. So for singly ionized helium, for Hg plus, what you will get? You will get Z equal to 2. Okay. And if Z equal to 2, then what you will write? Nu equal to 1 by lambda. Okay. And this is Z square. Fine. So 4 equal to 4 R Hg. Okay. 1 by nf square minus 1 by n square. Okay. I think you have understood this. Okay. If you think about the triply ionized beryllium. Okay. Beryllium plus. Okay. And what will you do? Then for that Z equal to 4. And if Z equal to 4, then you will get nu equal to 16 or Be 1 by nf square minus 1 by ni square. Okay. This will use this formula as possible. Fine. So here it is already said that the transition from a level which n equal to 7 to a level n equal to 6. Fine. So number 4, n equal to 7 to n equal to 6. Okay, I think it is already given. Fine. So I am going to use the same process. 1 by lambda equal to RH z square 1 by nf square minus 1 by n initial square. Fine. Okay, now input the values. Okay, and values has been already given to you. 1.097 into 10 to the power 5 into z is also given, and which is boron is 5, so 5 whole square. Okay, and this will be 7 to 6. Okay, so you will get 1 by 36 minus 1 by 40. I think it's clear. Okay, now use calculator. Okay, and if you use calculator, you will get ठीक है, 1 minute. Okay, what is given? The Rydberg constant is given already 1.0973 into 10 to the 5 centimeter inverse. Okay, this is given in MKS. Okay, sorry, CGS. Okay, if you need to write in MK, then you can write it by 10 to the power 7. Okay, you can write it. Okay, that's fine. And the difference between is 13 by 36 into 49. Okay, if you use calculator, then you will get 2021,669.50 angstrom inverse. Okay, and okay, sorry, meter inverse. Fine. If you now want to evaluate the value of lambda, then you will get 4946. Okay, sorry, 4946.4 angstrom. Okay, so this is our answer. Okay, now I am going to the next problem, and for this problem, uh, now check this. Okay, so this is the given problem. What is it said? That the wavelength of the second number of Balmer series of hydrogen is 4861 angstrom. Okay, no problem. Calculate the wavelength of the first number. Remember, okay. So this is not a hard task. Okay, first of all, I will use the formula for hydrogen-like atom. Okay, 1 by lambda equal to at RH into 1 by nf square minus 1 by ns square. Okay, I will use this, and after that, I will evaluate the value of RH, and after that I will substitute this. Okay. This is not a great job. Okay. So let's see. So question number 5. Okay, what is given? That the wavelength is given. I mean 1 by lambda equal to, we know, RH into, here z square is, I am not writing z square because this is hydrogen like atom, and for hydrogen z equal to 1. Fine. So 1 by nf square minus 1 by ns square. I think it is clear. Okay. Now we have already given lambda equal to uh, 4861 angstrom. It is given, and this is the Balmer series. Okay. And this is Balmer series. Okay, fine. So for this Balmer series, and this is the second line, second member. Okay. So for second member, the transition will be transition 3 to 2, because you all know that for Balmer series the transition from 2, 3, 4, 5, I mean 3 to 2, 4 to 2, 5 to 2, 6 to 2, and this will be from infinity. Fine, you all know this. So this is the, I think this is the second number of Balmer series. Okay, so there will be 4 to 2, I think. This I have written because first line is 3 to 2 and second line is 4 to 2. Okay, so this is 4 to 2. Okay, so now input RH 1 by 4861 angstrom, RH 1 by 4 minus 1 by 16, and if you calculate it, you will get 4861, okay, into 3 by 16 and 1 by RH, and if you calculate by calculator, okay, then RH you will get 10 to the power 8 by 91143. Okay, this is the Rydberg constant, and I will name this by 1, and after that I will use the second property, and it is given that calculate the wavelength of the first member. Fine. So wait 1 minute. Okay, so for first member transition will be 3 to 2. Okay, so same 1 by lambda equal to RH 1 by 4 because 2 square 2 to the power square minus 1 by 9 because of 3 to the power square, by 1 by 4 minus 1 by 9. And now I will substitute the value of RH. Okay, this is the value of RH. You can see already I have written number 1. Okay, so I will substitute the value of RH, and you will get 1 by 4861 angstrom, okay, into so 16 by 3 into 5 by 36. And if you calculate this, then you will get lambda equal to 6562 into 3 angstrom. So this is the answer. This is so easy. Now I will go to the number 6. Okay, so check this. Number 6, it is given that at what temperature will the average molecular kinetic energy in gaseous hydrogen, okay, so this is the important word, molecular kinetic energy in gaseous hydrogen, be equal to the binding energy of the hydrogen atom. Okay, this is quite mysterious, binding energy of the hydrogen atom. Okay, this is a great constant. Okay, the question is very much easy, but the concept is very much interesting. Fine, so let's solve this. Okay, before the number 6, I want to say something. So you need to know about the term binding energy. Okay, so binding energy. So what this word means actually, binding energy. So it is nothing but the energy required to break the nucleus, okay, and bring all the constitutions far away from each other. Okay, so what I am saying, that it is the energy required to break the nucleus and bring all the constitution far away from each other, and binding energy is the energy required to form the nucleus. Okay, this is also an example. Okay, so if you read the nuclear physics, then you will better understand. Okay, before that, you just need that binding energy is something. I mean, this is the energy to what is needed to bring the nucleus. Okay, fine. So this is the binding energy, and if you want to know more about them, okay, then you follow nucleus, and their binding energy equal to delta m c square. What is delta m means? This is the missing mass. What is delta m? A mass of the constitution, I mean total mass of the constituents minus actual mass of the nucleus. So this is the delta m and c square. You know all the. Okay, so use of it is. This is the basically. I mean, so this delta m. Okay, so this delta m. What this delta m? This mass goes. Okay, this is nothing but this mass. I mean this missing mass is basically converts to energy. So this is the binding energy. Okay, so delta actually B equal to delta m c square. Okay, so this is equal to the kinetic energy. So binding energy is basically equal to the kinetic energy. So this is equal to kinetic energy. Fine. So already you know that here I mean kinetic energy equal to 3 by 2 kT. I mean F by 2 kT. You all know for any system where F is the degrees of freedom, and for here 3 by 2 kT. Okay, I am considering, and that is already the reason, but I am not going to this part. Okay, so here F by 2, I mean F equal to 3, so 3 by 2 kT. Okay, this is the binding energy, and I mean kinetic energy, and binding energy is equal to total energy required. And for hydrogen atom, you all already know A equal to minus 13.6 z square by n square, and why z equal to n equal to n, so minus 13.6. This is the total mass, so minus 13.6 eV. And I am not here giving any minus consideration, I am minus term because I am taking the modifier. Okay, so minus 13.6 eV. Okay, and from here you can also know that K is equal to Boltzmann constant 1.63, I mean 1.2 what 1.638 into 1.38 into 10 to the minus 23, and you already know the, I mean you will get the value of t. Fine. So from here t equal to, you will get I mean equal to 3 by 2 into 1 by 38 into 10 to the power minus 23, okay, into t, and here minus 13.6. okay, and this is not a minus 13.6, this is in ev, so minus 13.6 into n plus 1.6 into 10 to the power minus 19 equal to 3 by 2 into 1.38 into 10 to the power minus 23 into t. And now denominator and numerator calculation, and you will use calculators, then t you will get t is 1.05 into 10 to the power 15k. So this is your answer. So this is the numbers. If you think this video is needful, then obviously share with your friends. Fine. And next video I will see you. Okay. Take care. Bye bye.